Let's answer question 12. So first we got to have the necessary imports. I'm going to load my IBM free account so that we can run the quantum circuits on the real hardware. So here we go. What code fragment codes the equivalent circuit if you remove the barrier in the following quantum circuit? So we have 1 qubit, and then we're going to measure it into classical realm at the very end. And we just do a Hadamard, a T-gate, a barrier, a T-gate, and a Hadamard. And I propose the barrier doesn't do anything meaningful, but we'll talk about the barrier later. So, which of these options encodes the same circuit without that barrier? Well, we can do this programmatically without having to know the math behind it by using Qiskit's state vector function. And in order to use that, we can't have any classical registers because a quantum state vector doesn't represent classical measures or anything classically. And so we can't have a classical circuit, classical register. So we're going to create it without any classical registers as an initial target, and we're going to use initial to represent the circuit that we can use the state vector function on. And then if we wanted to simulate adding a classical register to that quantum circuit, we could do it by creating a new quantum circuit with enough qubits at least to as there is for the one we're going to compose, the one we're going to add, basically concatenate from. And then we have our classical register, and we can name it so that way it's modular and will affect. So that way we can differentiate between the different quantum circuits. So using the compose function takes in a quantum circuit and adds all the gates from the quantum circuit that you give it to the target, or whatever one you composed it on. And that returns a new quantum circuit, so that way we have to assign it here. And then we can do that classical measurement and draw it. So let's make sure we did that correctly. Looks to be the same. Sorry. Alright. So that codes the target quantum circuit correctly. And we can create the different options for A, B, C, or D. Option A seems to think that T squared is equal to S. So in the tensor product, the quantum circuit can be written as the tensor product of all these operations, since that's the basic operation that combines these different gates. And so if we took out the barrier, T times T would be T squared, and we can see what other quantum gates might represent T squared. So maybe the S gate is equal to T squared. Or let's see, B is seeming to think that H squared and S and T squared is equal to the identity. Since, well, I know that H squared is equal to the identity, but maybe T squared is also equal to the identity. And if that was the case, then this would be the same as doing no operation. And C thinks that T dagger is equal to T, while H dagger is equal to H. So if T dagger is equal to T, then that would also be the identity, since the dagger is the same as its inverse. And so then that would mean B is the right answer as well, if C is the right answer. And D is thinking that the Z gate is equal to T squared. So let's get results from the real hardware, and we can compare them and see which ones gave the closest results as the target gave. So we can filter our backends using the least busy function, which will give us the least busy hardware. That will hopefully make it faster to run this quantum circuit. We can filter the backends, giving it a lambda function, and for that parameter we do specify. We can see if the configuration has enough qubits for our quantum circuit, and that it's not a simulator, and that it's currently operating. So we can execute all 5 of those circuits in one job to speed up the process, giving an array of quantum circuits and we give it the real hardware, and just for fun, let's use 2048 instead of the default 1024 for our shots. Alright, that'll send it off, and hopefully it's done by the time we're done with our classical analysis. So now we can do some classical analysis while we're waiting for the quantum results. And we'll use the state vector function provided by Qiskit to get the theoretical final result from each of the quantum circuits. So this gives us the final state vector if we perfectly, from zero initialization, performed all our operations mathematically correct. So the target seems to give us a 50-50% chance of measuring a 0 and a 1 with some relative phase. And I used the all close function to see if any of this iterator was equal to the target. So this creates the iterator, this is the list comprehension over all the different options we wanted to consider. So we can use SV as our variable to represent one of those. And then all close basically does equivalence, so is SV equal to the target? If so, return true. If not, if one of the elements is not equal within some absolute error, which I'll use the default, then it will return false. And looks like all the others are false except the first one. So that gave us an easy answer instead of having to visually look like we did here. So it looks like A is the right answer. And that means that the S gate is equal to T squared. So let's see if our real world results are done. Looks like it successfully ran, and now we can get our counts, and let's see them visually so it's easier to identify the true winner. Looks like, okay, our target is the blue one, and A gave us the closest answer, just like we thought theoretically. So option A is the right answer, and I've showed you two different ways, one with just measuring using the measurement results, and one that's using the Qiskit helper functions. But what does the barrier do? The barrier basically says wait for all other operations to be done before proceeding on to do the next operations that we'll specify. So it's like a barrier. It makes everyone stop and wait until everyone has caught up to any point that you specify. So if Q0 was doing a bunch of operations, and since if they're independent, the quantum computer can do those operations at any time it wants, let's say we really want to make sure that we do the X gate after these quantum circuits, these quantum gates. Then we would have to use a barrier, and we'd specify which qubits that barrier is across by integer, by list. And comparing that to one without the barrier, we see that the X gate is done as soon as possible. Since it doesn't care about what happened before in the sequence, since we were doing these independently, then it could do it as soon as possible. And so there we see the barrier make sure that all other operations are done before continuing on, if we really care about that. All right.